Today I will basically recapitulate what you have learned from your, from last three speakers. So that will basically act as a motivational aspect for what I am trying to discuss. Okay. So till now what we have learned is that our universe, that is basically homogeneous and isotropic at larger scale. So do you understand what you mean by homogeneous and isotropic? Is it clear to everybody? Okay. By homogeneity you mean there is no specific, no preferred position, and by isotropism you mean that there is no specific direction. Okay. So let us start directly from here. You have your universe which is homogeneous and isotropic. Isotropic. I add some term over here which is called at the largest scale, because this is what I am trying to focus on right now. And as you know, this can readily be described by a solution of Einstein's equation, and those equations you already know. So you are familiar with these things, I guess. You are familiar with these things. So this is the geometrical part and this is the matter part. This geometrical part, if you consider your background geometry to be homogeneous and isotropic, then this can be readily given by a maximal symmetric space, which is nothing but Friedmann-Robertson-Walker metric. Okay, so this is given by d squared. Am I audible to everybody? Can you hear me? Okay, fine. So this is given by d squared is minus dt squared plus a squared t dr squared by 1 minus r squared plus r squared into 2 space square. I write it like the omega 2 square. Okay, but this a square is basically, this a is basically called a scale factor, and this basically takes care of the expansion of the free space. Okay, so in cosmology this factor is really too important. As we will see, we will basically transform this factor to a different quantity which is called your Hubble parameter, but the meaning is all the same. Okay, so this quantity is very much relevant, and from geometry alone you can say that this k is your spatial curvature which can take, from geometry, which can take three values which are 0, plus, minus 1. Okay, as you will see from observation that k equals 0, this is the most favored preference from observation, but right now let us say that if you do geometry, then there are three options for k, which is 0, plus, minus 1. Okay, so this is all about geometry. And what about the matter part? The matter which basically gives rise to geometry, that is a perfect fluid. Okay, so for perfect fluid you know how to express T mu nu. I guess you have done these things. Please make sure that you have done these things. So is it clear to everybody? Because unless these things are clear, I mean you cannot understand what I am going to discuss. Okay, so this T mu nu part, that is basically given by rho plus p u nu minus p g mu nu, where p and rho, they are the density and pressure components of your perfect fluid. And if you impose homogeneity and isotropism over there, because as I have discussed, the universe is homogeneous and isotropic at larger scale, which is incorporated into your geometric part. So if you incorporate the same property in your matter part, that means if you assume that this T mu nu is also given by homogeneous and isotropic fluid, homogeneous and isotropic, then you are just left with the diagonal components. That is, if you impose these conditions, all the off-diagonal terms, they basically vanish, and you are left with T mu nu, which is nothing but rho minus rho p e. Okay, so in 4 dimensions you have just 4 components which are only diagonal components, and you don't have any off-diagonal component over here because you are considering your background space-time to be homogeneous and isotropic. Is this point clear to everybody? Okay, fine. So let's proceed from here. Can I use this board also? Fine. So if you start from here, you have your background Friedmann equation. So with this G mu nu, you just write down your background Friedmann equations. You know how to write down your background Friedmann equations. You know how to write it down. You have your background Friedmann equations. So you can readily write them down as the first equation is this, is 8 pi g by 3 rho minus k by s squared. So this is your equation number 1, and the second equation I write it like this is equation number 2. Okay, these are called your Friedman equations. On top of that, you have a conservation equation which is given by, so you have, along with that, you have a conservation equation, okay, which is your grad mu k mu nil equals 0. So this basically gives you rho dot plus 3 k dot by p rho plus p equals 0. So these are the three equations which basically govern your background geometry. Okay, and you can readily check that these three equations, 1, 2 and 3, given any tool, you can readily derive the third one using the other two. Okay, so you've done all those things in the last week, I guess. Okay, have you done all these things? Okay, so given any two equations, you can derive the third one. So this basically confirms that the system of equations you have, they basically form a closed system. So from mathematical point of view, when you say a closed system, you have readily a property that you have a unique solution. You basically guarantee a unique solution for it. Okay, so basically you have 1, 2 and 3, 1, 2 and 3, they basically form a closed system. Since you can derive any one using the other two, so this basically guarantees that you have a unique solution. Now, from mathematical point of view, telling that you have a unique solution for those equations, this is sufficient. But it has got a profound application in physics. So this basically guarantees that since solving these equations, you are basically trying to get a solution for AT, which basically gives you information about the expansion of the universe. Okay, so if you have a set of equations which gives rise to a unique solution, this guarantees that you were basically guaranteeing that you have an unique evolution of the universe, which should be the case because you have only one universe and that evolves uniquely. Now, if you have a background set of equations which basically with which you are trying to describe your system of equations, so now if it has got a unique solution, you are guaranteeing that whatever you are doing is perfect. Okay, so this basically guarantees that whatever solution you get from them, that uniquely describes your universe, whatever you want it to be. Okay, so that's it. So now how to do this thing, how to solve, so how to get into real life business. Let's just check. So observationally, so let's say forget about observations. So in practice what you do is that how to solve these equations. Now as you see that these three equations, though you have three equations which basically form a closed set, but these three equations highly non-linear. Okay, so it's not very easy to solve them directly. Okay, so how to do them? First of all, you consider a barotropic fluid. What do I mean by barotropic fluid? Barotropic fluid means pressure is function of density only. Okay, so if you consider a barotropic fluid, which fortunately our cosmic species are, okay, so if you consider a barotropic fluid, then you can readily write down your pressure, the relation between pressure and density like this. Okay, pressure is a function of density and I write down the functional form like this, where this is called the equation of state. So for simplicity, if you do that, and fortunately you can do that, your cosmic species support these kind of systems. So if you do that, and if you put this value back into your equation number 3, you can readily solve for rho. Okay, so that's a trick you do, and once you do that, your equation number 3 basically gives you rho is basically evolving with the scale factor as 3 into 1 plus omega. I think you have done this part as well. Okay, fine.
So why did you choose this barotropic fluid for the universe?
First and foremost, to make your life as simple as possible, once you choose barotropic fluid, you can solve those equations simultaneously. First and foremost, this is the mathematical purpose, and the physical purpose is what I have already stated, that fortunately you can do that because whatever cosmic species you have in the form of radiation, matter, or vacuum energy, all of them are barotropic fluids. So your nature permits you to do that. Okay, is it clear to everybody? That's good. So you solve these three, and now you have two equations, and in the right hand side you have expressed the parameter rho and p in terms of A. So now you have two equations with only one unknown A, and you can readily solve them. If you solve them, so if you put this value back into your either equation number 1 or equation number 2, okay, you can readily solve them, and the solution basically gives you AT. So you basically put this information in either 1 or 2, and this basically gives you your desert AT. Okay, this was our primary target. Okay, we consider different cosmic constituents, to put those values in T mu nu, and you find out AT. Okay, so this is the trick how you can do that. So once you do that, you can readily say how your universe is basically evolving with time. Okay, because as I said, this AT is the scale factor which basically takes care of the evolution of your free space. Okay, that's great. So now let us just consider some simple examples and see. So let us calculate for some simple cases. And these are very much physically relevant cases because the first case I am trying to discuss is my hot, that is relativistic matter. When in the right hand side, that is when for T mu nu, you have relativistic matter alone, which is very much the case when universe was really hot at very early time. Your universe was really hot, the temperature was huge. Okay, and that time most of the matter, they are basically made of relativistic kind of matter, and if you have relativistic kind of matter, then using thermodynamics you can readily say the relation between pressure and density is basically given by P equals rho by 3. Okay, so that is your equation of state. Omega is 1/3 from this equation. Omega equals 1/3, and if you put that value over here in this equation, let us call it equation number 4. So if you put your omega into equation number 4, this readily gives you rho raises a power minus 4. Okay? And if you put this expression into either equation number 1 or equation number 2, you can readily check that your scale factor AT is basically proportional to T power half. Okay? So this first of all guarantees that, let's take, if time increases, this parameter also increases. Okay, so this basically tells you as long as your universe was really hot, your universe has expanded. Your universe has expanded because the scale factor has increased during that time. So universe has expanded at a rate proportional to T power half. Okay, so this guarantees expansion of very hot universe. Okay, so now in course of time, when time passes on, your universe gradually cools down, and at some stage, at a very later stage, you have your universe is mostly made up of cold matters. Okay, so that is the case as of now. In present day, the temperature of the universe has gone down to a certain stage that all the matter, they are basically non-relativistic matter. So they are made of cold matter. So if you have cold matter alone, that is non-relativistic matter alone, then once again, for cold matter P equals 0, the pressure is almost 0, because that's why it has cooled down basically. So if your pressure is 0, it readily guarantees that your equation of state equals 0, and you put that value into equation number 4, that basically gives you rho raises a power minus 3, and then I'm doing the same business. Okay, there is nothing new over here. I'm putting a different value of omega and I'm solving those similar sets of equations with similar tricks. Okay. So this basically gives you rho by raised to the power minus 3, and you put that value into either equation number 1 or 2, that will give you 18. Okay. So if you do that thing, that will give you 80 proportional to t power 3rd. Okay. So this once again guarantees that your universe is expanding once again, but at a different rate than hot universe. Okay. So during hot universe the expansion rate was this, but during cold universe the expansion rate is this. Okay. So in general, how to solve those equations? So these are just simple examples, but you can generalize this further. Am I going too fast? Please warn me if I am going too fast. Okay, sir.
So the scale factor is a function of time, but in different eras of the universe, it changes. Is there a continuity between?
That's a pretty good question, and that's so I'll come to that point in a minute. Okay, I'll come to that point. Fine. So in general, you can just generalize these two solutions. Okay. So in general, you have okay. So in general, you can check that. So if you just put, so instead of doing all these things, if you directly put this value over here, and you can readily put this value into either equation number 1 and 2, you can see that the solution in general, the general solution is 80 proportional to t power 1 plus. Okay, so this is the general solution, and this basically tells you, you supply me one kind of omega, I will put that value over here, and I will readily say that this is the evolution of the universe. Okay, and this is what I call hot Big Bang cosmology. Okay. So in our discussions, we will readily encounter this term hot Big Bang cosmology. Okay. This basically tells you, so far as you have ordinary matter, whatever matter you see today, so far as you have ordinary matter, you can readily write them down as barotropic fluid given by this, and you can put that value over here to find out your rho t, and you can put that value in equation 1 and 2, the solution basically gives you this. So this basically guarantees that so far as you have your ordinary kind of matter, the hot Big Bang universe, that basically evolves like t power p, a power where p is less than 1. Okay, you can readily check for hot and cold matter, your p is half and 2/3. Okay, fine. And from observational point of view, you have done, I guess you have done a little bit of observational cosmology as well in the last week. From observational point of view, as I said, so right now, so why we are basically trying to make our life complicated? First of all, as I said, you have 3 equations which are highly nonlinear. So given a very simple form of rho, you can readily solve them. But unfortunately, our universe is not that simple. In most of the cases, you have an admixture of different cosmic species. So this is to answer to his question, actually. So you have an admixture of different species. Like if you consider present day universe, then you have little bit of, so right now I'm not giving you the exact estimates, and I'll come to that point later on, but you have a little bit of ordinary matter, whatever we see today in the form of luminous matter, you have little bit of dark matter, you have little bit of dark energy, you have little bit of curvature, you have little bit of radiation, and so on and so forth. So if you have an admixture of all these species, then your life is really, really complicated, because then you are not supposed to have an unique expression for omega. For different species, omega is different. So how you can really, so this basically makes your life, in the right hand side you have, so in the right hand side you have T mu, so you have different species sitting over there, and your equations are really, really complicated. So now your life is really complicated because no matter how much you try, you cannot directly solve them to find out explicit solution, exact solutions. So instead of doing that, what you do is that you write down the observable parameters directly from your equations and you try to probe those observational parameters directly from observations and you try to match those things. Okay, so now your job is a little bit different. Instead of solving, but you guarantee that you are basically doing the same business. Okay, but instead of trying to solve those equations directly, what you do is that you define observable parameters from those equations. Okay, and you readily define, recalculate rather your set of equations, and you define your observable parameters in such a way that they can be readily confronted with observational results. So now if you confront them with observational results, so now if you have a ground theory, you derive those observable parameters and you confront them with your observational results, and if you see that there is a very good agreement between these two, then you can guarantee that your background theory is correct. So this is your primary target, not to have exact solution, but to explain your universe. Okay, so this is what we are trying to do right now. Okay. And this is the primary target of doing observational cosmology. Okay, fine. So from observational point of view, what you do is that you don't try to directly find out AT. Instead, you try to probe this parameter H. I guess you know these definitions already. Okay, is it clear to everybody? Okay. So from observational point of view, you don't try to probe AT, but you try to probe HZ. What is your HZ? As I said, your H is A dot by A, I've already defined, and Z is the redshift parameter, that is the frequency change, frequency shift, okay, due to the evolution of the universe from the origin of a source of light, from the origin of a photon, till it has reached the observer, till it has reached us, okay. So this is the redshift, and this redshift can be readily written as A varies as basically 1 by 1 plus Z. Okay, you know these definitions, right? Okay, so please speak up. You know these definitions. Okay, fine, that's it. So from observational point of view, instead of finding out AT, what you do is that you try to find out your HZ. How? You try to find out your HZ by this equation, 1 plus Z minus dz dt. You can do that readily. How you can do that? Let me just recapitulate once again. You have your scale factor. So you expand your scale factor into Taylor series and take just a higher order correction, leading order correction, so to say. Okay. And then you can express everything in terms of this new parameter Hz, and this basically gives you, so this is the Hubble parameter today. This is the Hubble parameter today. From observational point of view, doing these things are really, really difficult. 1,000 times difficult than doing theoretical cosmology. Why? Because, so let's just motivate ourselves. I know you have already got motivations from your last 3 lectures, but let's just motivate once again. Why it is difficult to do observational cosmology? Okay, first of all, compare it with any other experiment in physics or engineering or whatever you call it. Okay, you have a readily made setup in the laboratory, you perform the experiment, once you fail, you perform it repeatedly, and you go on performing it, and you go on increasing the accuracy level and so on and so forth. Okay, but in cosmology this is really, really difficult, because what is the laboratory here? The laboratory is the universe. Okay, and the experiment that is happening over there is happening only one time. Okay, and even more difficult that you, the observer, whoever is measuring those things, that is residing today only. The phenomenon had happened, say, around millions of years back, but there is no such observer which observes that phenomena during that time. So different phenomena had basically occurred at different era, and we, the observers, are just sitting today, and we are measuring those observations sitting today. Okay, so first of all, you don't have time reversal, you cannot repeat your experiments, and secondly, you don't have any observer, you don't have any measurer who is basically residing at different era and measuring that phenomena. Okay, so this makes observational cosmologist life really difficult, but fortunately this human being, they are basically really brilliant. They have just found out a way out. Okay, so how to do that? So what they do is that observationally they just measure one quantity, the redshift, the frequency change. So observationally, the telescopes and everything, what they measure, so they measure different things, but the bottom line is that they basically try to find out the redshift. So from where the light is being emitted, oh, sorry. So from where the light is being emitted and that comes to the observer, the redshift of the frequency change in coming from that point to this point. So observationally we measure this quantity. Okay, and observationally we measure another quantity, that is all the cosmological parameters, values of all those cosmological parameters as of now. And then we just use our system of equations to track it back to time and find out all those parameters at different era. Okay, so this is the target of doing observational cosmology, and this equation is the first step in doing so. This basically tells you, you measure the Hubble parameter in that equation, which basically gives you the expansion history of the, so this doesn't give you the expansion history, this just gives you the expansion rate of the universe as of now, in which rate our present universe is expanding. Okay, and this is the redshift. This is precisely the information you gathered from different cosmological species. Okay, so you have different galaxies residing at different redshift. You gather all those informations and you put those values over there, and you can readily find out the Hubble parameter at different era. So you just utilize your Hubble parameter today, and you utilize your redshift values at different era. You put these values over here, that will give you the expansion history at different era, because this is H at Z. Okay, so that will basically give you the expansion history of different era, even if you are not an observer residing over that era and measuring that thing. Okay, is the point clear to everybody? So this is the primary target of doing observational cosmology, and observationally if you try to do that thing, first of all you can find out the expansion history of the universe at different era simply by using this equation. Okay, and secondly what you do is that, to answer to his question, if you have different cosmic species, so then instead of doing with rho, we define a new density parameter. So if you have a mixture of cosmic species, instead of defining rho I, we define a new parameter omega I, which is my rho I by rho C. Okay, but this rho C is this rho C is called critical density. I'll tell you in a minute what does it mean. Okay, so this is defined as 3h0 square by 8 pi g. Okay, so what I am basically doing, if you forget about all those things, this is the density required to have the k value, the spatial curvature value, to be 0. Okay, you can readily check from your Friedmann equation that if you put this rho C over there, you can see that k turns out to be 0. Okay, in your Friedmann equation, consider the first Friedmann equation, you have k equals 0. You put k equals 0, you will see the rho required to put k equals 0 is this. Okay, so this basically serves as not to put k equals 0, but to serve as a scale to measure the density. Like when you say this distance is 5 centimeter, what do you say? You know the unit of centimeter, you know this much amount of is 1 centimeter, and you say that this is basically 5 times of that unit, 1 centimeter. Okay, so this rho C basically supplies the unit of cosmic density. Okay, so whatever density you measure, that is this much times of this unit of cosmic density, and that unit is basically called critical density. Okay, so this is the first and foremost target of doing that you define, okay, you define a specific scale of measuring cosmic density, because when you measure density in the laboratory, once again, as I tell you, why observational cosmology is much more difficult. Okay, so when you say 5 gram, you know you have a spin balance and you measure. Okay, measure a mass and you say that this is 5 gram. But in cosmology, you don't have any such spin balance. You can't say that this much amount of matter is 5 grams or 5 kg. Okay, you cannot measure it with a spin balance. So that's why you say that you define a new scale which is called the critical density, and you measure every parameters in terms of how many times that density is with respect to the study. Okay, so this is one target, and the second target is, since this is a ratio of two densities, this new density parameter, that is simply a number. So you are not bothered about in which unit system you are working, whether this is gram or kilogram or whatever, you are not bothered about it at all. Okay, so you can just say its value is 0.25 or 0.3 or 0.7 and you are through. Because this is just a number. Okay, so this is the advantage of doing this, and if you do this, then so if you do this, then, so now in Friedman equations, in the right hand side you have different cosmic species. Okay, you have different rho i's sitting in the right hand side. I have written down all rho i's in terms of this new omega i's. Okay, so that sum over all omega i's, this is your total omega total. Okay, whatever species you can have, you just sum them up and you call it omega total. And if you put that value back into your Friedman equation, then your Friedman equation is given by h naught squared omega I 1 plus h. You can readily check. Okay, I think you have already done this. In Prasoon's lecture, I think you have done this. Okay, right. That's it. So what you can do is that in the right hand side, you put I equals 1, 2, 3, 4, 5, whatever you choose, whatever cosmic species your universe is made of, you put them thing, you dump everything in the right hand side. Okay, and you have this equation left for you. With omega curvature, you define, so you have a curvature parameter k by a square sitting over there as well. Okay, so for that curvature, you also define, you attribute a omega parameter over there, which is basically given by minus k by a naught squared, h naught squared. Okay. So from observational point of view, what we are trying to do is that instead of probing directly the scale factor AT, where is my duster? Oh my God. Your master equation, and we'll basically deal with this equation. Okay, so this is all about what you study in your hot Big Bang cosmology, and now the question I am trying to probe is that, are we content with whatever we have studied till now? Okay, till now means till in this class. Okay, because you have already discussed, I mean, you have already learned other things in the other classes as well. So till now what we have done is that we have proposed a background theory which basically explains your observable universe. Okay, first and foremost, should I be content with these informations alone, or should we learn other things? Now, an essential piece of information here is that, now doing cosmology, this thing has changed profoundly during the last 30-40 years or so. 30-40 years back, cosmology was a theory first subject. Okay, you didn't have anything observationally. Okay, you didn't have any a priori observable information. Okay, so whatever you do is doing mathematical calculations and forecasting things. Okay, you try to predict that this should be there, that should be there, this should happen at that time, that should happen at that time, and so on and so forth. But nowadays the thing is just the opposite. Now cosmology has become completely an observational first subject, because you have lots of telescopes, and which are basically, they are basically highly sophisticated telescopes, and they are basically giving you lots of precise information. Okay, so now a theoretical cosmologist's job is just the reverse. You have the observable information at your hand, you try to explain those observations from your background theory. Okay, so what are the observable informations do we have? So let me focus on cosmic microwave background information, because the theory I am going to discuss in this course is basically focused on cosmic microwave background observation. Okay, there are other observations as well, but let us focus on cosmic microwave background observation. So let us now focus on observation. Okay. Okay, first of all, let us try to find out which era it basically demonstrates. Okay, so it basically demonstrates high redshifts. Okay, so it discusses the physics of the very early universe. Okay, nevertheless, you can have information about the present day values as well. I'll come to that point later on. Okay, but first and foremost, it gives you information. So universe has evolved. Okay, throughout its evolution history, universe has evolved. This cosmic background basically gives you a snapshot of the earliest observable universe. Okay, you have this evolution history. In CMD, you see the earliest observable universe. Okay, what do I mean by early observable universe? In cosmology, suppose we have got, so once again, people usually have got some wrong information. Like, if I go on increasing the experimental sophistications, there will be an era when I can see the birth of the universe. This is a complete misconception. Okay, so this is the first and foremost misconception we should clear. Okay, I tell you that you can see up to certain level before which you cannot see. Why? Because
light has a finite speed. You won't travel.
Not for that, not really for that. This is the partial reason. Any other reason do we have? What do you mean by last scattering surface? This is the answer. So what do you mean by last scattering surface? Sorry? Okay, so but why didn't you see? So why can't you see before that? Sorry? Okay, that's the answer. So your answer is? Information. Which information? No. Okay, so let me just explain. So more or less we are correct, but let me just tell it in my words. The thing is that whatever you see today, when you see something, we see that basically what happens, that a photon basically comes from that that source of information rather, and that basically comes to me. Now, when can a photon travel? When it is completely free. Okay, but there was an era during the very early phase of evolution. You have already studied thermal history, so you know these things. Okay, there was an era when basically, so your universe was basically made of photons and baryons. Okay, and they were basically tightly coupled. Okay, they had interactions. They basically formed a soup of photon and baryon. So there was a time when you had basically photon baryon soup, and it was basically tightly coupled. Okay, but as soon as the universe started cooling down, when it cooled down to some extent, then atoms were formed. Basically, you had these free ions who basically come closer to each other, and atoms are formed. When atoms are formed, you have less free electrons sitting over there. Okay, so if you have less free electrons, then these photons, they basically try to move faster. Okay, and at some point it basically attains a speed which is called its free streaming speed. Okay, as soon as it reaches this free streaming speed, it does not interact, it just stops interacting with other particles. Okay, and it starts to move freely towards the observer, because there is no one to capture it. In other terms, you can say that there is a potential well basically formed due to this coupling of photon and baryon. And at some point, this photon attains sufficient amount of energy so that it can come out of the potential well. Okay, and there is no one to capture it, and you see that photon only. Okay, and this is called, what you say, this is perfect, this is called basically last scattering surface. Okay, so basically when universe cools down, you have basically less free electrons. Okay, so at some point photons basically they attain free streaming speed. Forget about these names, try to understand the physics. Free streaming speed, by free streaming speed means you have a potential well and photon basically comes out of that potential well. Okay, so now there is no one to capture the photon, and this is called the last scattering surface, the last time photon has captured with other particles, and you can see up to the last scattering surface. No matter to what sophistication you go on increasing your telescopes, you cannot see what happened there in beyond last scattering surface. Okay, so this is like what I call, so you can see up to last scattering surface. And this is what you see in CMB. Okay. But very important thing is that, as you know already, you have studied this thermal history of the universe. I will discuss other things as well. Lots of other things have happened before last scattering surface. Okay, and they have got, fortunately they have got reflection, they have got imprints of whatever they have happened on this last scattering surface. So last scattering surface basically acts as if this is some movie is going on there, and you are just seeing the screen over there. Okay, so in screen you are seeing say two-dimensional thing, and you are trying to predict what is happening before that thing. Okay, so you have this last scattering surface, you are seeing something is happening over there, and you are trying to predict from those observations, you are trying to predict what had happened earlier. Okay, and this is the real challenge, because now your life is really difficult. You are not seeing directly through observation what is happening. You are seeing its imprints, you are seeing the snapshots in last scattering surface, and you are trying to predict what has happened earlier. And you cannot say that I am not bothered about those things, because as I will discuss later on, that they basically govern whatever we see today. So they are basically responsible for whatever we see today. Okay, they basically form the seed of whatever you see today. So you'll have to see what happened earlier. Okay, so let's just see what information can we have from CMB. In CMB, so first of all in CMB, I think you have already seen it in Jayanti's lecture, so I'm just drawing the diagram. So in CMB you see a sky which basically looks like this. I'm very bad at drawing, so forgive me. Okay, so in CMB you see a sky which looks almost like this, which basically guarantees that our universe is homogeneous and isotropic at the largest scale. Okay, but you see very small inhomogeneities over there, and this is really interesting. Okay, so in CMB, so you have seen this image, right? Enjoy this lecture. Okay, fine. So you see more or less homogeneous and isotropic universe at largest scale. But on top of that, you see small inhomogeneities. I have 10 minutes on my hand. Let me quickly finish it. Okay, you see small inhomogeneities, and if you zoom it in, so these things is really difficult to handle. So let us just zoom it in a more usable language. So if you zoom it in, I think you have seen this plot also in Jayanti's language. This will be discussed in detail by Sheshadri. Okay, so let's just take the information and take it for our purpose. Okay, so if you zoom it in, then you can write them down in terms of temperature and isotropy, and you can plot this in terms of L, where L are the multipoles, and this part basically, this is the measure of temperature and isotropy, Okay, and you can see a plot which basically looks like this. Now, these basically encodes lots and lots of information. This is a very crucial plot. Okay, you have, along with this, you have other plots like polarization plots and everything. So, we will discuss those things in details. So, this basically gives you just the temperature anisotropy plot. And this temperature anisotropy plot gives you lots and lots of information. Okay, so let's just check what information can we have from this. Okay, so these are so our primary target will be not to explain the expansion history of the universe, but to explain it precisely. Okay, so just not to find out some scale factor, but to explain whatever you see there. Okay, these first of all guarantees that your background universe is not perfectly homogeneous and isotropic. This is the first piece of information you get. So you have homogeneous and isotropic universe at larger scale, but you have very small inhomogeneities. Okay, and this is the measure of small inhomogeneities. And why this is important? Because whatever structure we see today, like in the form of us, like in the form of stars, galaxies, clustered solar system, whatever inhomogeneities we see today, they would have formed from those initial homogeneous and isotropic universe somewhere. Okay, and this is where they are formed. This basically tells you at CMB, you do have, so your universe was homogeneous and isotropic before CMB, before last scattering surface. Actually, it was perfectly homogeneous and isotropic. Okay, but as soon as it reaches CMB, there are already small inhomogeneities which have generated somehow, I'll explain those somehow later on, which have generated from those homogeneous and isotropic universe. Okay, and that has evolved during the evolution history of the universe. As you know, the age of the universe is 13.8 billion years. So during this 13.8 billion years, those small inhomogeneities, they have evolved to form whatever structure you see today. So that's why I say CMB basically gives you a snapshot of the earliest possible universe, and at the same time it gives you a snapshot of whatever observable universe you see today. Studying CMB is that much important. Okay, fine, that's it. So let's just summarize what information can we have in CMB. And in CMB, you know, so let me just name those telescopes which are basically probing CMB. You will more or less, so yeah, I think you have already encountered these things in Jayanti's class. Okay. So what are the telescopes you basically probe in CMB? First of all, the earliest telescope is Kobe. Forget about the complete names and everything. Oh, let's just not bother about those things. So this is the earliest telescope which basically gave you the information that your background universe is not perfectly homogeneous and isotropic. There are small inhomogeneities sitting over there. Okay. So this is way back in 80s, early 80s, say, even before 80s. Okay. First proposition came in 82, theoretical proposition. It was even before that. Okay. Kobe. Secondly, a very interesting observation which is going on from 2001 onwards is called Wilkinson Microwave Anisotropy Probe, WMAP. And very recently, so it basically gives you data at 1 year's interval, basically, 2 years interval, so to say. Okay, there is a 1 year gap between subsequent data. Okay, so in 2001, that has basically given you, 2013, that has basically given you 9 years data. So this is WM9. The latest data is WM. Why I am telling you this, because frequently from the next class onwards, frequently I will talk about this WM9 and so on and so forth. Just keep in mind that these are basically the information. Okay, it has started running from 2001, and this 2013 they have given the latest data, which is WM9. Okay, fine. And in 2013 alone, there is a very different observation, which is Planck, which came from the collaboration of European Union, and that is basically its primary target is to find out more accurate data than WMAP. Okay, wherever there are limitations, and there is only one single year running. The result has already come. Part of the result have come. That is temperature anisotropy data. They have already published that data. I will come to that point later on. But they are yet to give you the polarization data and so on and so forth. Okay, those results will come later on. They have already run the telescope and it has closed the running, and now they are analyzing those data. those data are yet to come. Okay, fine. And there are some future telescopes. One telescope has already started running and given you some result, which is South Pole Telescope. It has already given you some result, but there are lots of other results yet to come. And there is Atacama Cosmology Telescope, ACT, and so on and so forth. There are other telescopes as well. Okay. What I am trying to stress on here is that not to puzzle you, but to give you information that lots of observations are going on in different parts of the world. So this is the high time of doing cosmology, because as I said, cosmology has become an observation first subject. So lots of observation and data are coming. So this is all about early universe. There are other observations for late universe as well. Okay, so forget about those things. For early universe alone, you have lots of observations coming from different telescopes. You have lots of data coming, or other data will come in near future, and your job as a theoretical cosmologist is to explain those observations in new cosmological analysis, so to say. Okay, and we will basically focus on these two results, WMAP and Planck, because they are more or less well established till now. Okay, fine. So given this, let us just summarize what information we have already gathered from WMAP 9 and Planck. Am I clear to everybody? If there is any problem, please feel free to interrupt me and ask questions. Any question? Am I going too fast? Okay. So what are the major information? From the next class, your life will not be that much easy, because whatever I am discussing today is just the recapitulation of what you are learning. But this forms the platform of whatever we will discuss from the next class. So let's see. Fine. But here lies the fun of doing physics. I mean, so you have lots of information, you're trying to explain those informations using your background knowledge and everything, and here lies the fun. So let's see how much fun can we have. So what is the major information? First and foremost information, as has been discussed time and again, I am sure, is that the CMB temperature, if you look back in time and you try to measure the temperature of this background homogeneous and isotropic universe, then you can see that in the low scattering surface, the CMB temperature is around 2.73 Kelvin at all directions. So this is the most crucial information you have, first of all. So if you look back in time, you see that as I said, for this initial homogeneous and isotropic universe, you can see that the CMB temperature, no matter in which direction you look at, okay, you see that CMB temperature is everywhere the same, and it's almost 2.73 Kelvin everywhere. Okay, so this is the first piece of information, and please keep this information in your mind, because while discussing this early universe phenomena, we will readily come back to these equations, these information. Okay, so this is the first and foremost information, and this basically guarantees our initial hypothesis that our universe is homogeneous and isotropic at the largest scale. Okay? Secondly, you see, as I have already discussed through this temperature and isotropic plot, that your universe is homogeneous and isotropic at largest scale, but there are actually small inhomogeneities sitting over here and there. Okay, so you have small inhomogeneities which are basically realized through temperature and isotropies. As I said, I am not talking about this polarization data and everything, because I am trying to focus on these things. Polarization will be discussed by Sheshanji and others. Okay, so you have small inhomogeneities, and they basically give you snapshots of cosmic structures. Okay. If there was no cosmic structures, what could have seen? You could have seen the perfectly homogeneous and isotropic universe everywhere. We should not be there. No one should be there. Okay, but since we are there, we see the snapshots of those things. I think I'll have to finish. Or 2 minutes. Okay, so let's just see. I'll take 5 minutes. I think I will finish. Okay, so this is the second thing. And third, what you see, that the age of the universe is around 13.8 billion years. So these are the pieces of information you see. And from the next class, basically, I will try to explain these informations using your background theory. Okay. And then what you see, I have already defined those dimensionless density parameters. You get the values of dimensionless density parameters from those data. I am not discussing from which point you will get which data because that will be discussed by session 3. Okay, so let us discuss the result that, say, using WMAP9, if you use WMAP9, I have discussed what WMAP9 means. So using WMAP9, what you get is that your omega total is around 1.0027. Your omega baryon, you have baryonic matter, which is around 0.63. You have dark matter, which is around 0.2402. I'm not talking about those error birds and everything. Okay, so these are the raw values. And you have your omega dark energy, which is around 0.7135. Omega radiation, which is around 10 power minus 5. And you have omega curvature, which is around minus 0.0027, which is almost equal to 0. Okay, and if you Planck values, then you will have little bit of difference in these things, but more or less the same values. So I am not talking about those Planck values. Okay, so in Planck you can have different values, but more or less they are just the same. Okay, fine. Next information what you get from CMB is, so information number 5 is, once again if you use WMAP9, you get the Hubble parameter as of now is 69.32. This is the value. Next, what you get is, I will discuss what I mean by this thing, but let's just take it as an information that we have nearly scale invariant power spectrum with small running. Don't get disheartened, I will discuss what I mean by power spectrum, I will discuss what I mean by scale invariant and so on and so forth in my class. So this is just another piece of information I get from CMD, that we get nearly scale invariant power spectrum, but this is not exactly scale invariant, you have very little running of that power spectrum. And at the same time, we have another information, forget about polarization information there, we have, say from Planck, so that is Planck comes into play over here, Planck gives you very important information, that in CMB, you see anomalies at large scale. What I mean by anomaly is that whatever prediction you should have, you basically get that your standard model, standard cosmological model, that is background A for W model, cannot readily explain those things. Okay, so what are the anomalies you have? We have two anomalies actually. One is around 10% deficit of signal at large scale. So this is what you get at large scale, okay? So there is a 10% fall of signal at large scale which cannot be explained using your Feldman cosmology. Okay, and at the same time, I will finish in a minute, okay? At the same time, you have your hemispherical asymmetry. What I mean by this? What I mean by this? As I said, this is your CMB sky, so you have two hemispheres, northern hemisphere and southern hemisphere, and you see whatever inhomogeneities you see, okay, they are not symmetrically distributed through northern and southern hemisphere. There are more cold spots in southern hemisphere, so there is hemispherical asymmetry. These two hemispheres, they are not just mirror images. One is not the mirror image of the other. So this is another thing which cannot be explained using your standard manipulations. Okay, So these are the points. So these were already there. These things were already predicted in WMAP as early as WMAP 1, but this is confirmed through by Planck. Okay. So this is the information you get in CMB, and so what you get at the end of the day is that you have your background cosmological model, which is Pilani equation. You know how to extract physics out of that thing, and you have your CMB results, which basically gives you this result. Okay, and these omegas and everything, they are also confirmed from intermediate and high redshift observations as well. So they are pretty much confirmed. So nowadays you are confirmed, whatever you are doing is perfect. Okay, and what you see is that using your background hot Big Bang cosmology, whatever predictions you can have and whatever data you have from CMB, there is a very large mismatch between these two. Okay, and this is more or less surprising because you are trying to predict your universe and you are seeing that this is fine up to a certain level. But when you come back, when you go back to your low scattering surface, you see a complete mesh-up between theory and observation. So in the next class, first of all, I will try to focus on what are the anomalies, what are the basically mismatch of theory and observation, first and foremost. And then I will try to modify our hot Big Bang cosmology in such a way that you can explain those mismatch. Okay, and that will basically form the platform of interest.